is about quantum key revocable dual RegF encryption revisited by Prapanjan Anand, Zihan Hu, Zikuan Huang, and Zihan is going to give the talk.
Okay, so I'm gonna to talk about this quantum key revocable dual RegF encryption. This is a joint work with Prapanjan Anand from UCSB and Zikuan Huang from Tsinghua University. So before I talk about what is revocable crypto, let me first give you an example when it is useful. So imagine two parties, Alice and Bob. Alice wants to attend our conference TCC here, but she knew that she is expected to receive some important mails during this week. So she asked Bob to take care of her mailbox while she is attending the conference here. Bob agrees, so Alice just sent the key to Bob. And after the conference, Alice asked Bob to return the key, and Bob returns the key. Everything looks fine until suddenly Alice realized that, if Bob is malicious, maybe he can duplicate the key, use some technology during the week, and after he returned one of the keys, he still has the ability to access Alice's mailbox. This kind of attack cannot be avoided in the classical world because every classical things can be copied in general. But revocable cryptography can help Alice from this attack. Okay, so maybe in the future, so again, it is by leveraging the non-clonal principle of quantum mechanics, but now the goal is to do this kind of delegation and then later revoke cryptography capacities enabled by some secret keys. So maybe in the future, when we have quantum computers, Alice can instead send a quantum key to Bob, and as quantum keys cannot be cloned in general, there's some code that we can design a scheme very cleverly so that Bob cannot access Alice's mailbox after he returns a quantum state that passed some check. Let me give some remark. So in previous talks, we have seen some like copy protection, and you may see that it is very similar to copy protection. In fact, it is very related, but it's a weaker notation than copy protection, because in this revocable cryptography, Bob is asked to return one of the bi-party state back to the honest party, while in copy protection, the bi-party state is on the adversary's control. And you may also record a notation called cryptography with certified deletion, but this notation is also weaker than cryptography with certified deletion, because honest Bob can return a quantum state instead of return a classical certificate to convince Alice. So to be more specific, in revocable cryptography, there is a quantum key where Bob can be used to do some cryptography task, and honest Bob, who always return the key, can always pass the check revoked by Alice. And for security, we hope that after sending a state that passed the check, Bob will no longer has the cryptography capabilities. So we have many interesting primitives in this area, like revocable public key encryption, revocable homomorphic encryption, and revocable PRF. And they aim at do the delegation and revoke the ability to do decryption and the ability to evaluate, etc. So in this revocable PRF, the quantum key is used to evaluate the pseudorandom function. And after you return the key that passed the check, the adversary can no longer distinguish the function from a truly random function on the uniformly random inputs. And our focus today is revocable public key encryption, so let me elaborate more on the syntax. So in this scheme, Alice first run the key generation to get some public key, master secret key, and a quantum key. She announced public key to everyone and sent this quantum key to Bob. And later, someone, Charlie, wants to send message to Alice, so she encrypts this increase the bits with the public key and announce the ciphertext. And we hope that with the quantum key, Bob can indeed do the decryption task. So Bob can recover this B. And later, Alice may ask Bob to revoke the ability. So if honest Bob returns this secret key, he can always pass the revoke check by Alice, which will use the master secret key. And for security, we hope that after sending a state, after Bob sending a state that passed the check, he can no longer distinguish the encryption of 0 and 1. And I want to emphasize here that the state that Bob returns and the state he keeps can be entangled in general. In previous literatures, we have many positive results, like we have assuming post-quantum PKE, there exists a revocable PKE scheme, and assuming some new conjecture, the dual reggae public key encryption scheme, a specific conjecture, a specific construction is indeed revocable. And we also have assumed post-quantum sub-exponential hardness of LWE. There exists another revocable PKE scheme with some classical revocation, which means that this time it is the same as in cryptography with certified deletion. Bob needs to send back a classical certificate. And it was asked in previous literature, can we prove that the dual reggae public key encryption scheme is revocable based on LWE? Before I answer this question, maybe you may already notice that we already have a revocable public key encryption scheme from this post-quantum PKE, which is the weakest assumption we can hope for. Why we even care about this dual reggae PKE scheme? This is because in previous literature, we already have some nice reductions from this revocable dual reggae PKE scheme that highly relies on the structure of the scheme. And besides, dual reggae is a textbook PKE that was taught in many graduate courses, and I think that studying this scheme can maybe inspire other problems with the similar structure. Okay, so here is our result. We proved that assume the post-quantum polynomial hardness of LWE over sub-exponential modules, the dual reggae public key encryption scheme is indeed revocable. And as promised, when combined with the previous reductions, we immediately get some nice corollaries. So we have the dual reggae public key encryption scheme has classical revocation, and also public revocable FHE and revocable PRF with quantum or classical revocation. The remaining of my talk will be the technical part. So first, let me explain what. So here it is the first revocable PRF from like concrete examples like LWE. And so what is the construction? Record that in the dual reggae public key encryption, the decryption key is just a short preimage X such that this AX equals to Y. And this preimage, this key can be used to decrypt the ciphertext using the equation below. And our quantum key is just a superposition of such short preimages. And Bob, with this quantum key, can run the original decryption algorithm coherently to decrypt. And to revoke, the Alice just used a short basis of the matrix A, and she can check whether the return state is indeed phi Y. So the honest Bob who returned this phi Y can pass. That's correctness, right? So how about the security? In previous literature, they assume that there's an adversary that can break the scheme. Then he returns the state on register R and the state on and keeps the state on register aux, such that it passes the revocation while the can use the row aux to distinguish later. And the previous strategy is just to extract a short pre-image x0 from the register R and another short pre-image x1 from the register aux. And as Bob can generate this phi y by itself, he can break the SRS if that works. And so how to extract the short pre-image x1 from aux? I don't have much time to explain about it, but they just go through them sequential hybrids and use the Gaussian collapsing property and the Gotthard-Rack-Levin theorem to get a short pre-image x1. And to get a short pre-image from the register R, it is easier. As you may imagine, if the revocation succeeds with high probability, rho y should have some non-trivial overlap with this phi y. So computational measurements leads to a short pre-image. So is it done? Not really, because what we need is to get x1 and x0 simultaneously. Well, in this strategy, it can be the case that both extraction succeeds with inverse polynomial probability. Well, they cannot happen at the same time. In previous literature, they overcome this thing by a new conjecture. And our contribution is another way to do the right extraction. So we begin by a test on the state rho aux to test if it's indeed a good distinguisher for the encryption of 0 and random element from the range. So here ATI stands for approximate threshold implementation. It is a way to estimate the distinguished advantage of a quantum state with only one copy of that state. And we got some inspiration from CGJL23 to do this guess entry by entry. And we come up with some clever, distributions with some nice probability, such that, so if the guess is correct, the test will pass with certainty, and if the guess is incorrect, the test will reject with certainty. In a word, if the first test succeeds, the second button works with certainty. And as the first test and the revocation pass simultaneously with inverse polynomial probability, we can indeed get two short pre-image simultaneously. So in conclusion, we remove the needs of a new conjecture from the previous literature, and we prove that the dual reggae public key encryption scheme is indeed revocable based on LWE. More details of the work can be found on InPrint, and thank you for your attention.